Now we know how to use the conditions for equilibrium. First condition, which states that all the forces are equal to zero. And the second one states that all the torques are equal to zero for external forces if the object is to remain in mechanical equilibrium. So let's go through some problems and see how we approach it and learn how to apply these two conditions. So again, um, zero torque doesn't mean that we're not necessarily rotating. It just means that the change in a rotational motion is zero. But again, for most problems, we are treating something at rest. So if it starts at rest, it's going to remain at rest. It's very important to create a diagram of the system. You want to have a free body diagram that not only includes the forces, but also includes your axis of rotation. Remember, if the body is stationary, it doesn't really matter where the axis of rotation is because it's not rotating. It is important, however, to choose an axis of rotation that's going to make your calculations easier. So we can apply the first condition first, then the second condition. Many times it's actually better to apply the second condition of equilibrium first because we can place it at a location where one of the forces is going to go away and then use that to solve for some of the other unknown forces. So it seems sort of backwards, but in many of these cases, we're going to do the second condition of equilibrium first and the first condition of equilibrium second. You could go in any order, but I think for simplicity, it's usually easier to start with the second condition of equilibrium. So let's start with something really simple. This is the bicep and how it acts on the forearm. We, of course, know that there's a bicep muscle, which causes the elbow joint to flex. There's also a tricep muscle, which is in the back, something that we're not going to talk about here, which causes it to extend. But if we hold a mass in our hand, that is going to create a downward force that is going to create a clockwise torque, which the bicep is going to act against. The bicep is going to create a counterclockwise torque to oppose that torque. And of course, there's also going to be additional forces, what we call a reaction force at the hinge at the elbow joint. Now, reaction forces are very common in these different systems, especially if we have some system which relies on a hinge to keep it together. Here, the joint pretty much acts like a hinge. Other systems, such as a hanging sign, we'll also see have hinges associated with them. So notice what I've done here. I have the applied weight. I have this ball, which I'm supporting, which is 50 newtons. I indicate its distance from what I choose to be the center of rotation, because my reaction force is going to be at the elbow joint, which is a natural place where I'll choose the hinge to be the axis of rotation here. And then, of course, I can choose the bicep muscle to be, the opposing the effort against the load. And that will be a distance of 0.03 meters or 3 centimeters from the elbow joint. Okay. Now, again, I could have used the axis of rotation to be at the location of the bicep. I could have put it here, but it's the reaction force that I don't know. I know the least amount about. So I'm going to put my axis of rotation out there, and naturally, that is a hinge there. Okay, so notice I'm doing the second condition of equilibrium first. The torque due to the reaction force plus the torque due to the force from the bicep plus the torque due to the 50 Newton weight, all of these are going to be equal to zero. Okay? Of course, the reaction force produces no torque because its moment arm is zero. For the bicep, its moment arm is 3 centimeters. For the weight, its moment arm is going to be 35 centimeters. Now, very importantly here, we have to be consistent with the direction that we choose. It is convention to have counterclockwise rotation to be a positive torque and clockwise rotation to be a negative torque. And you've seen I've done this here for tau F and tau W. So my reaction force goes away here. I only have one unknown. Okay, that's the force of the bicep. I can calculate that. And for a 50 Newton load, the bicep has to exert 583 Newtons because its moment arm is less than a factor of 10 of the load that I have here. So its mechanical advantage is greatly reduced. But again, we know that this is basically because the bicep only can contract a small amount. This creates a much larger range of motion for the elbow joint, even though mechanically it's disadvantaged here. So bicep exerts 583 newtons. Now I apply the first condition of equilibrium. This is going to give me my reaction force. I basically didn't have any X forces here, any forces in the horizontal. The bicep pulled up, the load pulled down, okay? If this elbow joint were at an angle, that would not be the case, but I've taken the simplest condition here. So my reaction force will all be in the Y direction. So the sum of the forces here has to be equal to 0. So we've got to cancel out those other vertical forces. So F minus R minus W is going to be equal to 0. The bicep force is pulling up, the weight or the load is pulling down. So because the bicep force is so much greater than the load, we also need an additional downward force from the elbow joint, and that comes from the ligaments that actually hold the joint together. So again, I solve for my unknown. I know my weight. I've found my bicep force, and I see my reaction force is 583 newtons minus 50 newtons, or 533 newtons. Now, the ligaments exert almost as much force as the bicep, but it's important to note here that the ligaments can't do any work, okay? They just create a reaction force, a force that reacts to the forces on it. Only the bicep can actually do work here, but of course, this is a statics problem. The mass is not moving, so no work is being done by the bicep. All right, let's take a look at another problem. And this problem is a problem. I have multiple images that have been moved around, but I have a man walking out on a beam. The beam is attached to a wall, and then it's also suspended by a cable, which creates tension at 53 degrees. So, because my original diagram isn't all that great, I'm going to jump right to my free body diagram. And you can see here, here's my different loads. The man is going to have a weight of 600 newtons at 1.5 meters from the wall. The weight of the beam is 300 newtons, okay? And finally, we have an unknown tension. We do know the direction that the tension is pulling, and we do have a reaction force, which we actually don't know its magnitude or its angle. Okay, so I can identify really three different pieces of information, three different independent pieces of information that I don't know. I don't know the magnitude of the tension. I don't know the X component of the reaction force, and I don't know the Y component of the reaction force. So again, let's do the second condition of equilibrium. I've chosen my axis of rotation to be where the beam connects to the wall. Even if that isn't a hinge, I can still be the axis of my rotation. I like, doing the axis of rotation on the reaction force because I want to get rid of that and just calculate any of my unknown forces using the first condition of equilibrium. So second condition of equilibrium. So again, the second condition of equilibrium states that the sum of the external torques is equal to 0. There's going to be no torque due to the reaction force. There's going to be a torque due to the weight of the beam, a torque due to the weight of the man, a torque due to the tension. I apologize here, there should be tension, and that's going to be equal to 0. So looking at this, Again, no torque due to the reaction force, so that comes out. The weight of the beam happens at 1/2 the length of the beam. The beam is 5 meters long. The weight of the man happens at 1.5 meters. These two torques are negative because if I look at this, they want to rotate the beam in the clockwise direction. If you think about this, if I were to cut the tension, cut the cable here, this beam would rotate in this direction. The torque due to the cable is going to be the perpendicular component, so Ty times 5 meters. You could also write this as just tension times sine 53 degrees times the distance from the axis of rotation, 5 meters, which we do later on, but really it means the same thing. The y component of the tension is T sine theta. The torque of that tension is RF sine theta. So it brings us all to the same thing. So now I'm just plugging numbers. This, of course, is 0. Here is the weight of my beam times its center of mass, okay? I assume that it's, uniform, so its center of mass is going to be half its length. Here is the man's weight times his position from the axis of rotation. And here, of course, is my torque due to that tension. Again, tension is unknown here, so I'm trying to find the tension here. And of course, I'm happy because the reaction force has gone away. So negative 750 Newton meters plus negative 900 Newton meters gives me 1650 Newton meters. So T times 4 meters equals 1650. I divide both sides by 4 meters, and I get that the tension of the cable is 413 newtons. Now I can do the first condition of equilibrium, and this will help me solve for R. Now remember, there are two components of R I don't know. I don't know the X component, and I don't know its Y component here, okay? Of course, I could do it in polar coordinates too. I could say, I don't know its magnitude, I don't know its angle. But because I've been using Cartesian coordinates anyway, in terms of the Y's direction gives me the direction of the weight, I'm going to just stick with X and Y here. So the sum of the forces in the X direction, only the reaction force and the tension are going to have an X component. The two weights do not. I know that the reaction force has an X component because the sum of the force in the X direction has to be equal to 0, and there is an X component to the tension, okay? There's no X component to the tension. I'd end up with 0 for Rx anyway. So, I have to go through this. But clearly there is an X component to the tension, so there's going to be an X component to the reaction force. Rx is unknown. The X component to the tension, if I look at this, it's pulling in, the negative X direction, so it's going to be negative T cosine 53 degrees. So 413 newtons from my second condition of equilibrium times 0.6, which is the cosine of 53 degrees. And that gives me an Rx of 249 newtons. So I have the X component of the reaction force here. Now I do the Y component. I just have two additional forces. I have the weight of the man and the weight of the beam that I have to include in this. I've already calculated Ty earlier. Ty is the force of T times the sine of 53 degrees. Sine of 53 degrees is roughly 0.8. Negative 413 times 0.8 plus 900 gives me 570 newtons. So now I know all my forces. I know the tension force, I know the reaction force. If I want to find the magnitude of the reaction force, that's pretty straightforward to do. If I want to find the angle, I can find that too. The angle, of course, we can use inverse tangent. We take the Y component over the X component, and we see that it's actually about 66.4 degrees. Okay, and okay, that pretty much agrees with the way I originally drew the diagram. So I'm happy with that. And of course, if we wanted the magnitude, I'm surprised we didn't calculate the magnitude here. We want the magnitude again. We take Rx squared plus Ry squared, and that would give me roughly, I don't know, about 650 newtons. Okay. All right. Let's take a look at this. A uniform ladder of 10 meters long, weighing 50 newtons, rests against a smooth wall, as in the figure. If the ladder is just on the verge of slipping when it makes a 50-degree angle, what does this mean? It means that this frictional force has reached its maximum value, okay? Remember, friction is less than or equal to mu times n, okay? So we're at the maximum value for friction, so friction now equals mu times n. Find the coefficient of friction between the ground and the ladder for this condition. So if I increased the distance between the foot of this ladder and the wall, it would begin to slip, which means that if I had an angle less than 50 degrees, it would just start falling or slipping down the wall is really what it's doing. And we're going to say that there's no frictional force between this part of the ladder and the wall. Okay, so let's do this calculation. One thing you should notice here is, okay, I picked this as my axis of rotation, okay? I could have picked this as my axis of rotation, that's fine. But I'm picking this as the axis of rotation, and that's going to make two of these forces disappear in the second condition of equilibrium. But we've got to be careful here. Notice that this weight right here, the torque is not simply the weight times the distance, okay? Is a 10-meter ladder. It's going to be uniform, so 5 meters is where this is acting. We have to take into account the angle that this makes with respect to the ladder. So if this is 50 degrees, this angle is going to be 40 degrees. Likewise, the wall, this angle is going to be equal to this angle. The torque due to the pushing force from the wall is going to be the distance, 10 meters, times the force, P, which is unknown, times the sine of 50 degrees. So here our torques are a little more complicated to calculate. Got to be careful there. So let's go ahead and do this. We're going to actually start with the first condition first. We could have started with the second condition. I think it's easier to start with the first condition. We'll do the X forces first, and then we'll do the Y forces. It makes the most sense to start with the X forces first, but Y forces first. But I'm going to start with X. So sum the force in the X direction. Again, I'm going to keep my my coordinates, pretty standard. Vertical is going to be in the Y direction. Horizontal is going to be the X direction. Only the frictional force and the pushing force in the X direction. So F is in the positive X direction. P is in the negative X direction. They're going to be equal and opposite. I know that my frictional force is at its maximum value, mu times N. So this just gives me a relationship for the coefficient of friction. It says that mu is going to be P divided by N, the pushing force divided by the normal force. Remember, we want to find the coefficient of friction between the ground and the ladder. Well, here, my pushing force is unknown. My frictional my coefficient of friction is unknown, and my normal force is unknown. So I have three unknowns. I'm going to have to use everything from the first condition of equilibrium. I'm going to have to use the second condition of equilibrium here. So now that I have a relationship for mu, let me use the Y direction, first condition of equilibrium, to find the normal force. That's easy. Weight pulls down, the normal force pushes up. N minus W equals 0, N equals W. If the ladder weighs 50 newtons, then the normal force is 50 newtons. So I have the first part of this. Now I'm going to find my pushing force, but I'm going to do that using the second condition of equilibrium. Okay. If I choose my axis of rotation to be right here, The normal force and the frictional force do not contribute to the torque here. So once again, I have the torque due to the weight of the ladder. Remember that this is 40 degrees here, okay? Got a 90-degree triangle. 50 plus 40 plus 90 is 180. And up here, we have this angle is equal to this angle. You should know that from geometry. And again, WRL times sine theta gives me this torque for the weight. It wants to rotate the whole thing in the clockwise direction. PRP sine 50 degrees gives me my counterclockwise torque due to P. So here I take, again, my torque from the weight, my unknown torque from the wall. I see that P is my only unknown here. P becomes 161 Newton meters, the torque from the weight divided by its moment arm, which is 7.6 meters, and I get 21 newtons. Remember, the distance from the axis of rotation is 10 meters, but when I take 10 meters and I multiply it by the sine of 50 degrees, I get the moment arm. So P is 21 newtons. I'm going to now plug that into my first equation, okay? Use P over N. Normal force is 50 newtons. The pushing force from the wall is 21 newtons, and I get a coefficient of friction of 0.42. Here's another one. This is very similar to the problem that we did before, just another one that you can try out to test to see if you know how to do this. Again, think about where you're going to put the axis of rotation. It makes the most sense to put the axis of rotation where the reaction force is. We don't know the magnitude of the tension. We know its angle. Rx and Ry are unknown. So for the best economy in terms of the best use of mathematics, put the axis of rotation there because you don't know Rx and Ry. And again, we just go through the same procedure, okay? We do the second condition of equilibrium first. We have a torque from the weight. We have a torque from the tension, all right? Here, we also have an additional weight from the sine hanging down. So tension, weight 1, weight 2, weight 1, of course, is the weight of the bar supporting the sine. Weight 2 is the sine itself. And of course, the torque due to the tension is RT times sine theta, okay? And again, once I've calculated that, I can put that in my torque equation. Here's the torque of weight 1. I'm sorry, weight 1 is the sine, weight 2 is the beam. But in any case, the weights create a clockwise torque, okay? That doesn't always happen, it just happens in this case. The tension creates a counterclockwise torque. I put in all the torques in my equation. I solve for my tension. My tension is 509 newtons. We've done the second condition of equilibrium. Now we can use the first condition of equilibrium to find Rx and Ry. Sum of the force in the x direction equals 0. Only Tx, I should say only the tension has an x component, Tx, other than Rx. So our sum of the forces are going to be Tx plus Rx is equal to 0. This gives me my component for the reaction force in the x direction. It just opposes the x component of the force of the tension. The y component, we've got to include all the different weights, the weight of the sine, the weight of the beam, okay? The y component of the tension upward. So Ry minus 50 newtons from the beam, minus 200 newtons from the sine, plus 215 newtons from the upward component of the tension, gives me an Ry of 35 newtons. So again, we found out all our unknowns. We didn't know the magnitude of the tension. We didn't know Rx. We didn't know Ry. We used the 3 different equations to find our unknowns. And again, if you want to find out the magnitude of R, you can just use the Pythagorean theorem. R is equal to the square root of Rx plus Ry squared, Rx squared plus Ry squared. And if you want to find the angle, it's just inverse tangent, the Y component divided by the X component. Okay. And again, change the angle, forces are going to change. Okay. Here's a similar problem. Again, similar approach. Put the axis of rotation at the hinge. That's where Rx and Ry are. Do the torque first. You can pause this video if you want to, see this completely. Now that you know how to do it, do the X component to get Rx, do the Y component to get Ry, and then again, you can get if you want to find out the magnitude of R, use the Pythagorean theorem. If you want to find the angle, use inverse tangent. Just one more to show you. In this case, this person's standing out on a plank. Instead of having a reaction force, they've actually created a tension of two ropes, a vertical rope and a horizontal rope. And then we have a third rope, I should call T1 here, creating a tension in this direction. So this plank to support the weight of the person and the weight right here. And this behaves like the other sign problems, except for you notice that the tension is going off in this direction rather than in this direction. Again, nothing crazy about this. Treat it just like the other sign problems. Use the second condition of equilibrium to find tension 1. Okay, once you have tension 1, you can use the sum of the forces in the x direction to find the tension in 3, sum of the force in the y direction to find the tension in 2. And basically, as long as you don't have more than 3 unknowns, you can solve for these problems. Here's a little bit of a change up. And again, if you want to go back through those videos, you can reverse. If you want to go back through those problems, you can reverse and pause the video. Here's sort of another change to the problem. Rather than just calculating straight out forces, we are going to look at a ladder with a weight of 50 newtons. It's going to be climbed by a person of 100 newtons of mass. That's a really small person. People don't weigh that much. Probably should have used weigh that little. Probably should have used a much bigger weight there. But in any case, let's do this. The ladder is 10 meters tall, has a coefficient of friction of 0.6 with respect to the ground. If the ladder makes a 50-degree angle with respect to the ground, how high can the person climb before the ladder slips? So your job here is going to be looking at this. I know W1, okay? I know W2. My unknown, instead of a force, is this distance here. So let's think about this. I don't know the normal force, okay? I don't know the frictional force. And instead of not knowing a force, I don't know the distance of W2, and therefore I need to calculate that as an unknown. So how do I approach this problem? Well, again, I'm going to put my axis of rotation down right here. I'm going to start with the second condition of equilibrium like I've done in the past. W1, W2, and the pushing force all create a torque. So let me calculate these two torques first. This is a 50-degree angle, so this is a 40-degree angle, another 40-degree angle. So torque 1 due to W1, torque 2 due to W2 are negative 161 Newton meters and negative 64 newtons times X meters. I don't know what those are. And of course, I have to include the torque from the pushing of the wall. Again, I don't know the pushing of the wall, but that's going to create a torque in the counterclockwise direction. It's going to be a positive torque. These were negative torques. Okay, so it's going to create a positive torque. And again, that's going to be 50 degrees because that matches this angle here. Okay, so I have two torques with two unknowns. I put them in this equation right here. And obviously I can't solve for this equation, okay? This is an unknown, this is an unknown, but I get a relationship between this and this, all right? Now, how am I going to solve for this x? Well, x is equal to whatever the pushing force is, times 0.12 minus 2.5 meters. Okay, let's take a look at this. We'll do the first condition of equilibrium. We'll do the sum of the force in the y direction. The two weights pull down. The wall contributes nothing here. So they're going to be equal and opposite to the normal force, which I probably would have guessed 150 newtons. Now I'm going to do the sum of the forces in the x direction. The normal force is 150. The frictional force right before this slips is mu times n. Okay, so F minus P is going to be equal to 0. So I get a pushing force of 90 newtons. Okay, so now I can plug that back into this equation here. 90 newtons times 0.12 minus 2.5. I get 10.8 meters minus 2.5 meters. You can climb up to 8.3 meters before the ladder starts slipping. Now, again, 100 newtons is not a realistic weight for a person. It's probably going to be much greater than that. So if I had a greater force there, they probably wouldn't be able to climb as high. And that's why it's very important when you're going up a ladder, that the higher you go, the less stable it becomes based on whatever frictional force you have on the base. The ladders themselves have little cleats, which you have soft ground, it can actually grab into it, or rubber feet, which can be rotated, which is a pretty high coefficient of friction. But again, as you climb higher, eventually you're going to get to a point where the ladder can't support you anymore. If you are of greater mass than the ladder, which most people certainly are. Okay. So again, in approaching these problems, very important, find out where you're going to put your axis of rotation. If you have a problem with the reaction force, stick that axis of rotation there. There are some situations where you might have to choose it differently, but for the most part, it's usually the reaction force, since we don't know the x and y component, that you want to have the axis of rotation about.